Okay, welcome back. In the previous videos, you learned the basic notions of what is a vector or what is a matrix. Why do we care about vectors? How can we turn non-mathematical objects like a document into a vector? How we can use that to measure the distance between these non-mathematical objects like documents, how close the content of these documents are. So we realized that knowing how to deal with vectors is very useful. We also introduced the most basic notion of separating a space into two pieces, a hyperplane. What is classification? Classification is splitting the space into two pieces where if observations would fall on either side, then you would classify them as 1 or 2, or as -1 or +1. And one key quantity is the distance from the hyperplane, because the hyperplane is meant to be a border between the two true categories, whether it's fraud versus non-fraud, whether it's spam versus non-spam, or whether it is about classifying reviews, movie reviews, into positive and negative. And why does it matter to measure? Because each observation, you can think of it as a point in this n-dimensional space, as we saw in that London Review article. Okay, so we have this hyperplane here. It's defined by this x transpose A equal B. And then we have this arbitrary point z, which can be on this side or that side. And we have this dz of z and h, which is essentially, for us, it means the distance of this point z from this hyperplane h. That is the objective of this video lecture. How do we find this based on A and B? Now, as a side note, there is something that we can do. In other words, we can get the same hyperplane with different A's and B's. How? By a simple rescaling. Let's imagine alpha is a positive constant. You can think of it 2, 3, whatever. Now, if this is one of the hyperplane we are considering, if we just multiply A with alpha and B with alpha, we still have the same hyperplane. Because we are multiplying both sides with alpha, nothing essentially is changing. So there is this scaling flexibility, which essentially there are pairs of A and B's that are the same hyperplane. Okay. Now, let's draw this figure. This is our hyperplane. This is our arbitrary point z. This is our point x0, which we specifically defined in the previous lecture. It's the vector that goes from the origin to the hyperplane, and it's orthogonal to it. So this vector is the length of this vector is the shortest distance of any point on this hyperplane to the origin. And the distance of this hyperplane to the origin is the length of x0. So we have the z, and then the distance we are looking at is this length. We are interested what this length is. Now, this is orthogonal to the hyperplane 2, so if we continue this line is parallel to this line. So this line is parallel to this line. So this length is the same as this length. So we can find this length, this one. This is what we are interested in. Now remember A and x0 from the previous lecture are pointing in the same direction. Now we can create something like a hat. That's something that people do to make a vector out of the original vector that is pointing in the same direction but has a length of 1. That's why the hat comes on top of it. And you can obtain such vector by taking this vector and divided it by the length of it. Why is this unit norm? You can just easily show it. The L2 norm of a hat is the square root of a hat transpose a hat. A hat is a divided by the length of a. And since this is a scalar, the transpose doesn't affect it. The only transpose will only affect the vector. So you have a transpose divided by the length of a multiplied by a divided by the length of a. So you have a transpose a divided by length of a squared. And a transpose a is nothing but length of a squared. So this is 1, so the length is 1. Okay. So you may say, why do we care about it? We care because we want to find this distance, and in order to find this distance, we have to find this whole distance and then subtract this distance from it. So from here to here, we find it, and then from here to here, we subtract from it, so we get from here to here, which is the same as from here to here. Okay. From here to here is the length of x0 we found in the previous lecture. From here to here, we don't know. It depends on z, but what we learned about the cosine essentially tells us that this length is nothing but this length multiplied by the cosine of this angle. This is something we learned in the previous lecture. Now remember, how did we find the length of A? A transpose x is norm of A times norm of x times the cosine between A and x, but A and x0 are pointing in the same direction. The angle between them is 0, so the cosine of 0 is 1. This is equal to b, so the length of x is b times the norm of A. This is from the previous lecture. Why do we care about that? Because that's this length. Now the next thing is we need this whole length, and then we can subtract it, and what remains is this part. Okay. So let's decompose this vector z into two orthogonal parts, z orthogonal and z parallel, such that these two are orthogonal to each other, so the inner product is 0. Z parallel is parallel to x0 and a, z orthogonal is orthogonal to them. So the distance of z from h is the length of z parallel minus the length of x0. The length of z parallel is nothing but the length of z times the cosine of this angle theta, minus, and then here we have this. So what is this cosine of theta? Well, we know that A transpose z, remember A is the same direction of x0. So the angle between z and x0 is the same as the angle between z and A. So A transpose z is norm of A, norm of z, cosine of the angle in between. So the norm of z times the cosine of the angle is nothing but A transpose Z divided by length of A. So we can take this and put it here. And then we have that 2. So the distance of Z from H is A transpose Z divided by the length of A minus the norm of x0. The norm of x0 was nothing but B times the length of A. So the distance of a point with a hyperplane is just A transpose Z minus B divided by the length of A. So recall that this is the hyperplane, and let's say x is on edge, so x is on the hyperplane. Now the question is, what is the distance of that point x from the hyperplane? Well, it should be 0 because it's on the hyperplane, and if you put it in the formula, we get 0 because dx from the hyperplane is x transpose A minus B divided by the norm of A, and x transpose A is B, so we get 0 as expected. Now, is this a signed distance? In the sense that if the point is on one side of the hyperplane, the distance will be positive, on the other side it will be negative? And yes, based on what we learned in the previous lecture, if a point x is on one side of the hyperplane, x transpose A is greater or equal than B. If it's on the other side, it's less than equal than B. And if it's on the hyperplane, it's equal to B. So dz, let's say z is an arbitrary point, is A transpose x minus B divided by the length of A. So on one side of the hyperplane, A transpose x, which is the same as x transpose A, is greater than B, meaning that this distance is positive. Whereas on the other side, x transpose A is less than B. X transpose A is the same as A transpose X, so the distance becomes negative. So this is signed distance, and that is very helpful. As we will see in the next lecture, we use the signed distance with the labels, and then we assign labels as positive and negative 1, and then these two will fall into place and make this classification problem we turn it into a geometrically interpretive. In other words, I will illustrate the geometrical interpretation of classifying points based on hyperplanes. But the take-home message here is how to calculate the distance. What is a hyperplane? What is a half space? How to find the distance of a point from the hyperplane, and understanding that this distance is signed. So on one side it's positive, on the other side it's negative.